So in the last session we discussed the modal analysis for forced vibration response or modal response history analysis. It was based on the idea that if we use the mode shape matrix to transform the governing equation of motion from u to q coordinates, some new coordinates, the resulting equation of motion which we get in new coordinates is uncoupled, and we can take out each equation separately, solve it separately if we are given with modal properties, and then we can transform the solution back to u coordinates or physical coordinates. So this simplifies our solution of equation of motion greatly. All we need to do is to just first calculate the capital phi matrix. That is the main matrix which is used in this modal RHA. That matrix helps us in transforming our governing equation of motion. That matrix also helps us in bringing the solution back to the original physical coordinates. So this method is called modal RHA or modal time history analysis. So it is the forced vibration analysis now. Any given loading, any given q of t vector, you can solve for any given multiple degree of freedom system using this method. Each equation which you take out from the uncoupled matrix equation, that equation resembles the equation of motion of a single degree of freedom system. So we have defined quantities like modal mass, modal stiffness, modal force. So each mode of a multiple degree of freedom system is governed by an equation which is like equation of a single degree of freedom system. So it's like we are decomposing multiple degree of freedom system into modal single degree of freedom systems, many modal single degree of freedom systems. So as I explained in last session that if for example you have a 10-story building, it will have 10 modes. You can mathematically decompose that 10-story building into 10 separate modal single degree of freedom systems. So you will have 10 SDF systems, each will be having a different time period. Actually those time periods will be the time periods of that multiple degree of freedom system. And each modal SDF system will be governed by one equation which will be that uncoupled equation which we get from modal RHA. So if I can represent the whole idea graphically, it's like if I have, let's say, a 3-story building or a 3 degree of freedom system, I have decomposed it as a sum of 3 single degree of freedom systems, this plus this plus this. See, so each one of them have a different time period, let's say T1, T2 and T3, 3 modes, and these T1, T2, T3 will be basically the time periods, 3 time periods of this multiple degree of freedom system. So T1, the first modal SDF system, will have a mass equal to mu1, where mu1 is mathematically equal to phi1 transpose into mass matrix into phi1 vector again. So you only need the first mode shape vector to calculate mu1, obviously the mass matrix also. It is subjected to a force equal to capital R1 of t, and it has a stiffness equal to mu1 omega 1 square. Similarly mu2, mu3, right? So you apply any dynamic forces, a set of dynamic forces which is represented by the capital Q of t vector. You apply that vector there to the actual multiple degree of freedom system, or you apply R1, R2, R3 to these modal SDF systems and sum their responses, you get the same response as you apply that Q, capital Q of t. So this is, let's say, applied with R3 of t. The relationships between R1, R2, R3 and the capital Q is this one, that R vector containing R1, R2, R3 is equal to the capital phi matrix transpose times Q of t, right. So you convert the actual mass of the multiple degree of freedom system into modal masses using these equations. You convert the actual stiffness of the multiple degree of freedom system into modal stiffnesses, and you convert the actual Q vector applied to multiple degree of freedom system into R vector, which is actually the modal forces, and you solve each SDF system separately to calculate its own response denoted by small q of t. So this application of R1 of t to this SDF system will give Q1 of t. Similarly, this will give Q2 of t, and this will give Q3 of t. And finally, you can arrange them to construct the Q vector, which is Q1, Q2, Q3. The responses of the individual modal SDF systems. And then you finally take the Q vector back to U vector by using the original transformation equation, which is U is equal to capital phi into Q of t. So Q vector is again transformed back to U vector physical displacements of your multiple degree of freedom systems. So this is an overview of modal response history analysis, and no matter how complex the structure is, you can always mathematically decompose into sum of many SDF systems. Now theoretically, the number of those single degree of freedom systems is equal to the number of modes or the number of degrees of freedom mathematically, but the simplicity involved in this method is that you don't need to consider all number of modes and combine all modal SDF systems to get the response which is accurate enough. You only need to combine first few modes. So for example, if you have a 5-story building, maybe the combination of the responses from first 3 modes or 2 modes is enough, because increasing higher modes, adding their contribution to the U of t more and more modes may not increase the accuracy of your total solution, because the contribution of higher modes keep on reducing as you go more and more number of modes. So the contribution of third mode towards U of t will be less than the second mode. Similarly, fourth mode will contribute lesser than third mode even, right. So considering fifth or sixth mode, adding it to total U of t will not increase your accuracy much. So you only need maybe first 3 modes or 4 modes, that is enough for most of the cases. So which means that the modal SDF systems, only 3 or 4 SDF systems is required. Solving 4 single degree of freedom systems and combine their response to get U of t may be enough for a 10-15 story building, right. So a 1000 degree of freedom system can be boiled down to 3 or 4 modes only, or 3 or 4 modal SDF systems. So you apply a real earthquake, for example, or a real Q of t vector to your actual multiple degree of freedom system, which is like 1 million degree of freedom system. It may take several days to run maybe, but on the right hand side you have just 3 single degree of freedom systems which are subjected to 3 modal forces. So a single degree of freedom system, it can be solved in just a matter of few seconds, right. So on the right hand side you just have a very simple representation of the same complex structure. So you apply the same earthquake to those 3 modal SDF systems, and sum their responses, you get the same response as you apply the earthquake to the very detailed mathematical model, the complete detailed multiple degree of freedom system. So it means in commercial programs also, if you set the analysis option to modal RHA, it should take significantly less analysis time compared to the direct integration, for example, right. The direct integration solution is based on the idea that we can step by step solve the whole governing equation by keeping it in its original form and then converting it into incremental form. On the other hand, this method makes use of phi vector or phi matrix, right. So this is simpler, this takes significantly lesser analysis time even for very complex structures. Let us take one example, that for example we have a uniform cantilever beam which is idealized as a 3 degree of freedom system as shown here. So you have mass m1, m2, m3 which is lumped at 3 different locations along the length of that beam. So actually this cantilever beam is a continuous structure, it is actually infinite degrees of freedom system, but we, for the sake of simplicity, we assume it to be a 3 degree of freedom system having 3 lumped masses, and the degrees of freedom corresponding to those 3 masses are let me rename them as u1, u2, u3, right, because I changed the notation from this figure. So u1, u2, u3 are 3 degrees of freedom. So it is just like shear building, but it is like rotated in horizontal manner. So it is simple a shear building, it can be treated as a shear building. So u of t vector, which is u1, u2, u3 are the 3 displacements of these 3 masses. And first let us treat the case of free vibration response undamped. So mu dot dot plus ku is equal to a null vector. This modal analysis or modal RHA, although we have formulated it for forced vibration case, we will see that this is valid for free vibration calculations also, because the right hand side or the modal forces in our modal single degree of freedom system equations will be 0 in this case, and therefore the same method can be, same framework can be applied to free vibration also. So let us first see the case of free vibration, that this is a 3 degree of freedom system, and m1 is m over 6 where m is some constant mass, m2 and m3 are m over 3. So if you take m common, you will be having this whole thing as mass matrix, and this is the stiffness matrix. Let us say that these are given already. So we are given with the mass and k matrix, and we are required to first calculate the free vibration response using this modal analysis. We have already derived an equation for free vibration response, and that is u of t is equal to sum of phi I into ai into sine omega I plus theta I. So we already know that the free vibration response is sum of the contribution of all mode shapes. So for I equal to 1, you will have first term of this series, I equal to 2 up till I equal to the number of degrees of freedom. So phi I is mode shape representing the shape of that particular vibration, and this whole function is a time function actually. So actually if you see, this thing is q of t for free vibration case, this time function. So although we have that expression already and we can calculate free vibration response using this expression on top right, but let us apply the same forced vibration framework, that uncoupling and everything, let us apply that to free vibration case also, and we will see that we will get almost the same equation, or actually the solution method will converge to the same solution method which we have seen in the free vibration case also. So, this is M and K matrices, and let us say they are given. Obviously, the K matrix will be the function of material property, the function of cross sectional property, and the function of whole element property, which is length. And let us say the first step is to perform modal analysis, and let us say we are given with the mode shapes and natural time periods also. Otherwise, this will be the very first step of your modal RHA to determine capital phi matrix, which means phi 1 vector, phi 2 vector, and phi 3 vector for this case, and determining the omega 1, omega 2, omega 3. So, the eigenvalue analysis is already carried out, and for this demonstration, let us say that we are given with the mode shape 1, mode shape 2, and mode shape 3, and their natural frequencies also. So, mode shapes are normalized in this particular example as the first entry, the roof entry, or the element corresponding to U1 is set equal to unity, right. So, mode shapes are normalized already, that the roof number or right end number is already 1, and other two numbers are relative to that. So, phi 1, phi 2, phi 3, they are given already. So, we have already the capital phi matrix. From here onwards, the actual analysis will start. The forced vibration or free vibration also can be covered in this. So, first check the free vibration case. Obviously, in order to have some free vibration, we must have some initial conditions, otherwise there will be no free vibration. So, the initial conditions which are given for our free vibration case is that u of 0 vector is some u1 of 0, u2 of 0, and u3 of 0, which is 3, 2, and 1. If you plot that, it will become this kind of a configuration, that the first u1 at a time t equal to 0 is having a displacement of 3 units, whichever units you are using. This is having 2 units and this is 1. If you join them, you get this kind of a deformed shape. So, the u of 0 vector is given and u dot of 0 vector is also given, that is all 0, 0, 0. So, it is like you have displaced the beam in this deformed manner and then release it, and now it is starting vibrating freely, and you are required to calculate the response. The response will be actually 3 functions, u1 of t, u2 of t, and u3 of t, right. If you can determine u vector in this against this initial conditions, that is a free vibration response. So, the very first step will be that we will convert the initial conditions given in the physical coordinates to the initial conditions in the generalized coordinates. So, we will be calculating q of 0 and q dot of 0. So, the initial conditions can be transferred or transformed into the generalized coordinates. So, we will be using the same transformation equation, but obviously this time we are converting u to q. So, therefore, the equation will be capital phi inverse times u of 0, right. So, this is the same equation, u of t vector, bold vector, is equal to the capital phi matrix times q of t vector. So, I just rearranged it, and for t equal to 0, this will be the term. So, phi inverse is calculated already, inverse of a 3 by 3 matrix, you can sort that out, and then u of 0 vector, you carry out that multiplication, you get this vector. So, this is actually the first entry is q1 of 0, second entry is q2 of 0, and this is q3 of 0. So, these are 3 new numbers, and you cannot relate them physically now. For example, you cannot plot them like this, because these 3 numbers are not the initial deformed shape of the structure in q coordinates. They are not physical coordinates, they are generalized coordinates. So the initial conditions, the initial displacements in q coordinates are calculated already. Similarly, you can do it for initial velocities, but since all velocities are 0, when you multiply 0 0 0 with a matrix, you get again 0 0 0. So in q coordinates the initial velocities are also 0, but the initial displacements are different numbers, different than 3 2 1, right. So this is clear. The next step would be to extract the modal equations, obviously, modal SDF systems. We know that when you uncouple the equation of motion using this transformation, the modal SDF system is this. In case of undamped case, you have already seen the modal SDF system. This is equation 31. This is simply the modal mass of ith mode times modal acceleration, you can call it modal acceleration, plus modal mass times the modal frequency square times the modal displacement is equal to the modal force. So this equation 31 will always be true, obviously, but you have to write it for your specific structure. For any ith mode undamped case, this will be the modal equation. So let's write it for our case. We are having a 3 degree of freedom system, so we will be getting 3 modal equations, I equal to 1, 2 and 3, and those 3 modal equations for free vibration case will have 0 on their right hand side, because we know that r of t vector is actually what? Capital phi transpose times the q of t vector. Q of t vector is all 0 0 0, right. For free vibration case, q of t is all 0 0 0. So which means r of t is also all 0 0 0 when it is multiplied, right. So which means that there will always be 0 on the right hand side of modal equations when you are dealing with the free vibration response. So the free vibration response modal equation will become this. Obviously you will be having mu I here and mu I here also, but when you have 0 on right hand side, you can cancel that mu I, right. So the modal equation will be very simple for free vibration case. It will be simply qi dot dot plus omega I square qi equal to 0, and I will be 1, 2 and 3 for 3 modal SDF systems, right. So we can write that equation for 3 SDF systems or 3 modes, and the general solution for any ith equation, let us say I write it for you, q1 dot dot plus omega 1 square q1 of t equal to 0. This is the first equation. Similarly q2 omega 2 square q2 of t equal to 0, and similarly q3 dot dot plus omega 3 square q3 equal to 0. So these 3 equations we get already, and first equation solution will give us q1, second equation will give us q2, third will give us q3. So I write here this solution for any ith equation. I can be 1, 2 or 3. We know already that this is very simple equation, and let's go to chapter 1 of our course, and there we already solved for the free vibration response of a single degree of freedom system. In our case, q of 0 is 0, q of 0 is given by 3 numbers which are shown in the, you can say, last slide, q of 0 vector. So we know what is q1 of 0, q2 of 0, q3 of 0. So the initial displacement for all 3 equations is given. The initial velocity for all 3 equations is all 0 0 0, right. So we can apply now, because now let's take out one equation. We have the free vibration equation for a single degree of freedom system, and the initial displacement and initial velocity, they are also available to us in q coordinates. initial displacement is given, is calculated already, initial velocity is 0. So let's put these initial conditions to the free vibration response of single degree of freedom system, and that will become our Q of t, right. So if you remember, the free vibration response u of t of a single degree of freedom system was what? It was u of 0 cos omega t plus u dot of 0 something function of u dot into sin omega t, right. When initial velocity is 0, you will not have the second term. When initial velocity is 0, if you remember, you will not have second term, you will only have this as a solution if you only have initial displacement, right. Can you relate that? Can you remember? Free vibration of a single degree of freedom system, that equation. So let's apply that solution to each of these three equations one by one. So for any ith equation, the solution will become qi of t, the initial displacement for that particular q, q1, q2 or q3, times cos of omega I into t. So actually this is three equations, three solutions, I equal to 1, I equal to 2 and I equal to 3. We already have what is q1 of t, what is q1 of 0, q2 of 0, q3 of 0, that is calculated already here, right. So let's just put the initial displacements in this solution and replace omega I with first omega 1, then omega 2, then omega 3. You will get these three solutions. So you arrange them in the q vector. So q vector is q1, q2, q3. q1 will be simply the q1 of 0 times cos omega 1 t. Similarly q2 of 0, q3 of 0. So everyone is clear how we get this q vector now? So what we did is that we solve the modal SDF system. In this case it was for free vibration response, but if we have any forced vibration case, then you will have some forces on the right hand side, and then you will be using the corresponding response equation for the forced vibration. This was the free vibration response, so we use the free vibration of SDF solution. So q of t vector is calculated already. Now let's bring it back to u of t by multiplying with the capital phi matrix. So this is capital phi matrix times q of t vector, it will give you u of t vector, right. So you carry out the first row and this column, you get the first entry in the resulting vector. The first entry in the resulting vector is what? u1 of t. Second entry will be u2 of t, third will be u3 of t, right. So u1 of t is what? 1 times first number plus 1 times second number plus 1 times third number. That whole thing will be equal to u1 of t. So u1 of t is written here as this first number times 1 multiplied by this, plus 1 multiplied by the second number, so it is again the same thing, 1 multiplied by the third number, it is that same thing. So this whole expression containing three terms is equal to u1 of t. Similarly you carry out the multiplication, second row this column, third row this column, those will be u2 and u3, right. So that's how you will finally get the expressions for all three displacements of all three masses. This was the free vibration response. u1 is the displacement at the beam's tip, right. So u2 will be the middle one and u3 will be the other one. So if we plot the first term in u1 alone, what is it actually? It is a harmonic function with a frequency equal to omega 1. Now omega 1 is the lowest frequency, so you can plot it like this. It will be having some frequency omega 1, so it is a harmonic function with omega 1, and the amplitude of that function is 3.353. So if this is the mean line, for example, this peak amplitude is what? 3.353. 353, and the frequency is some omega 1. Omega 1 is already calculated. Obviously, the very first step is to calculate these omega 1 and phi vectors. So omega 1 is given already, it is already the function of properties of that beam. So which means that you can plot that first term in your u1 of t. Similarly, let's plot the second term that is having an amplitude far less than the first, which is 0.421, and it will have a frequency which is omega 2. Omega 2 is higher than omega 1. So for the same duration, if we plot, we will have more number of cycles, but the amplitude will be lower. The third term will have a frequency omega 3 and the amplitude is even lower. If it had fourth mode, it would have a frequency even higher and an amplitude even lower. So actually the first term is representing the contribution of first mode towards u1, then second modes towards u1, third modes towards u1. All three are harmonic functions with different frequencies. When you sum them, you superimpose them. For example, this is omega 1, this is omega 2, this is omega 3. When you superimpose three frequencies, the one which has the highest amplitude, the overall resulting function will follow that trend, but on top of that it will have local fluctuations which are contributions from omega 2 and omega 3. So the overall solid black line, which is the sum of these three signals, the overall solid black line is following overall omega 1, but at the same time it has local peaks which is following omega 2 and then omega 3. So you can see that overall it is following similar to omega 1, but in one cycle it has these peaks which are actually the contribution of the second term or second mode, and even within one small peak you have even lower smaller peaks which is actually omega 3, the signature of omega 3. So if you plot in Excel maybe for any time t equal to 0 to t equal to, let's say, 20 seconds, you will finally get the combined, you can say, fluctuation u1 of t, but you can even plot individual terms to see what composes the response, how the response is made of actually. If you want to suppress u1 of t, you should focus more on first mode, because that has the highest contribution towards amplitude. If you suppress first mode's contribution, you suppress the overall response, right? So several of the insights you can get from this analysis, but I'll keep my discussion up till here. I mean, I will not go into those details, those practical aspects. This trend is not necessary that it will always be followed. It depends on initial condition, because see, this is free vibration response. So whatever u1 of t is, it is free vibration response of the first story or tip of the beam, right? It depends on the initial configuration also. If I deform the building in initial configuration which resembles second mode, the building free vibration will have the highest contribution from second mode. But this time, this particular example, I give an initial deformation which resembles first mode shape. Isn't it so? That this deformed shape is similar to first mode shape. Let me go back and show you this is the first mode shape. So I deform the building which is similar to first mode shape, and the resulting free vibration is telling you that the first shape will have the highest contribution. If I deform it in the second mode shape and then let it vibrate freely, it will have the highest contribution from second mode shape. In case of ground shakings, always, most of the times the first mode shape is excited the most, right? So the effective earthquake forces are not that they give some initial conditions which is resembling second mode shape or third mode shape, right? So just imagine a structure and you shake the ground. So the first mode shape naturally will dominate the response, right? If the building is regular and if building is typical. I cannot say that it will be true for all cases, but mostly the first mode shape has the highest contribution. Like if you quantify in terms of amplitude, you can say 60-70% of the displacement response is coming from first mode, 20% is coming from second mode, and maybe less than 10% is coming from third mode in one particular direction. When I say first, second, third, I don't mean that software numbering. I mean that first mode in X, first mode, second mode in X, third mode in X, right? So first three modes I mean in one particular direction. They may be mode number 1, 4 and 9 in software numbering, or they may be mode number 2, 6 and 8 in software numbering. So when I say second mode, third mode, I mean these shapes. It doesn't mean software numbering second or software numbering third, right? Similarly, now you can work out the U2 also. This row multiplied by, sorry, the second row multiplied by this column, then third row multiplied by this column will give you U2 and U3. So these will be the expressions for U2 and U3, and you will find the same trend. If you plot individual terms and combine, you will get the similar trend. So U1, which is the first story displacement or displacement of the tip of the beam, is being composed from all three modes. So this is a point which I am making clear right from start in all lectures, that first mode doesn't mean something related to first story only, right? All three omega 1, omega 2, omega 3, they are being combined to make first story displacement, and they are being combined to make second story displacement and third story displacement, right? So mode shape is a concept which is different than you can say one particular story level or one particular degree of freedom. First mode is the first mode shape will be having all entries corresponding to all degrees of freedom, right? So it's a shape of all along the height. Now let's so now by the way, you know two methods to have free vibration response. One is the same original method which we started actually, where we actually derived that equation. U of t vector is equal to sum of phi I ai sin omega I t plus theta I. This was the original equation which we derived while solving for free vibration response. This is the case where we discovered the concept of mode shapes or natural frequencies, right? Now we know another method, and actually if you think closely, it is the same method. See, this is what it is telling you, that each term of this summation is a contribution from any ith mode. So I equal to 1 to capital N maybe, where N is the number of modes. So each term is actually what is that term actually, because here we have sine, here we have cos, so basically they are convertible. Sine and cos both are harmonic functions. Here we have a constant number being multiplied by that sine function. We have that constant number here also, or this whole thing, right? And this is the contribution from first mode phi I. So this whole thing is oscillating with a frequency omega 1 or omega I, then omega 2 or omega 3. So actually each term in that solution is one term in the same summation series. So both of the solution methods are actually same. The first method we directly derive this expression, and second method we use the transformation concept and uncoupling concept to get the final solution. Both of the solutions will be same, right? Now let's go to forced vibration case. Now some forces are applied to our same beam. So now our governing equation of motion is this one. Some q of t vector is given. This is actually u vector. This is u vector. It is not one function. So actually it is u1, u2, u3, and each of u1, u2, u3 will be composed of actually this series. So actually this, when you multiply this phi1, phi I actually, that will convert this thing into a vector. See, actually you are having a time function multiplied by a vector. So the resulting thing is a vector, right? So the multiplication of that vector entry times the AI is a constant number, which is actually this number, right? So both of the solution methods are actually same methods. One is that we derive it using the mode shape concept, and second is that we uncouple, use that uncoupling approach and then transformation and then get the free vibration case. So now our q vector is actually some q1 of t, which is applied here, the first degree of freedom. Let me rename these degrees of freedom as u1, u2, u3. So at the place of u1 there is a q1 of t force applied, and that is an impulse load or step load. So from 0 it reached to a certain number fa, and then it stays there, right? So it is a dynamic force called step force, and the response will be same as the response of a rectangular impulse. The difference is that rectangular impulse come back to 0, but this remains there. So actually both of them are the sudden increase in force from 0 to a certain number. So it can be treated as a step force, a dynamic force. So q1 is applied to our degree of freedom number 1, but no forces are applied to degree of freedom number 2 and 3. So the capital Q vector which we can make is q1 of t 0 0, right? And q1 of t is a step force. It is this force. It is a dynamic force, and the force was once 0, and within no time it increased to a certain number. Now q1 of t could have been harmonic also, it could have been periodic also, or any other impulse loading, or it can be random also, it can be a numerically defined loading also, right? So it doesn't matter your resulting equation, single degree of freedom system equation, you can handle it, you can handle the most complex case for SDF system also. So in our case it is the impulse loading q1 of t, and other two loadings are 0. So this will make our q of t vector, right? So now it is a non-zero vector, and we are talking about forced vibration of that beam. The modal equation will become this. The modal equation will not, now mu I will not be cancelled because right hand side will have a non-zero number. That number is actually r I of t. I can be 1, 2 and 3. Very first thing is that we calculate these omega, this mu I modal masses, and we know that modal mass are the diagonal entries of this matrix capital phi transpose times m times capital phi again. So you get mu1, mu2 and mu3. You can carry out that complete multiplication, or you can simply do first mode shape times mass matrix times first mode shape again, transpose of first mode shape, that will be mu1. Then you can do for second mode shape, and that will be mu2, and similarly mu3 also can be determined. Or you can carry out that complete matrix multiplication, and diagonal entries will be actually your modal masses. So mu1, mu2, mu3 are calculated already. Omega 1, omega 2, omega 3 are given already, the modal analysis results. Now we have to calculate R1, R2, R3, the modal forces for our 3 single degree of freedom systems. Now we know that R of t vector is what? It is phi, capital phi transpose times q of t, right? So capital phi is what? Capital phi is a 3 by 3 matrix now, which is having phi 1 as our first column, phi 2 as our second column, and phi 3 as our third column. When I take transpose, it will become actually the first row will become phi 1, second row will become phi 2, and third row will become phi 3. When this matrix is multiplied by our q vector, which is q1 of t force 0 0, when you take that multiplication, you get a resulting vector which will be this one. Our q1 of t is fa, and fa is representing that impulse force. But please don't confuse with it that it is not a static force, it is a dynamic force, because it was once 0 and it suddenly increased to a certain number. So it is a dynamic force. So when you carry out that multiplication, you will see that the first mode shape is being multiplied by q1, by this q vector. The first entry of first mode shape multiplied by q1 plus all other entries are being multiplied by 0 0. So only the first entry will be this one, the first entry of the first mode shape. Similarly, when you carry out second row with this column, the first entry of the second mode shape times q1 and all other multiplications are 0. So second entry of the first entry of the second mode shape. So when I say phi 1 2, I means the entry number, and this 2 is the mode number, right? So first entry of the second mode shape, first entry of the third mode shape times fa. So this is the modal forces vector r1 r2 r3. So this is r1, this is r2, this is r3, right? So now you know that although the second and third degree of freedom were not having any physical forces, but their modal SDF systems will have non-zero forces, because now when you write the modal SDF equation, it is this one. For r equal to 1, you will have first r1, r equal to 2, you will have the second number, r equal to 3, you will have the third number, right? So all three equations for I equal to 1, 2 and 3, all three equations are forced vibration equations. So everyone get that point, that although actually no force was being applied to our physical coordinates in u2 and u3 degree of freedom, but when we convert into q1, q2, q3, all three have the applied force now. So you can write that equation for I equal to 1, this will be the first entry of first mode shape. When you write it, the I equal to 2, first entry of the second mode shape, and similarly third entry of first entry of the third mode shape. Similarly, omega 1 will be omega 1, 2 and 3, mu will be mu 1, 2 and 3, right? So you will get three equations. Actually this thing is three equations of single degree of freedom systems, three single degree of freedom systems, each subjected to impulse load, because by nature when you multiply that impulse load by a constant number, first entry of a mode shape, it will again be an impulse load with a different amplitude, right? So each of the entry in the r vector r1, r2, r3, each of r1, r2, r3 is an impulse load, although actually we had one impulse load applied to u1 degree of freedom, but now we have three impulse loads, three modified impulse loads applied to q1, q2 and q3, right? So this equation I write again and keep on writing again, that equation, it is an equation of a hypothetical SDF system which has a mass equal to mu I, which has a stiffness equal to mu I omega I square, and which is subjected to r I of t. Now r I of t for I equal to 1 is this number, I equal to 1, I equal to 2, I equal to 3. In all three cases the r force will be an impulse force. So let's assume that we have 0 0 initial conditions, because this is the forced vibration case. So let's keep our problem simple and let's assume 0 0 initial conditions. So the 0 0 initial conditions in u coordinates will give 0 0 initial conditions in q coordinates, right. So our q of 0 is 0 and q dot of 0 is 0. Now we already know the response for an impulse load. Response against an impulse load is equal to P naught over K times 1 minus cos omega t if we ignore damping. If you remember that impulse response chapter, this was the response we have determined already for an impulse having a height equal to P naught, right, which means for each I equal to 1, 2 and 3 we can apply that response to this equation. It is just the matter of application of that equation for I equal to 1, 2 and 3. So generally for any I can write it as Qi of t, the response of this equation which I just encircled, the response Qi of t will be, this whole thing is what, P naught, the amplitude of the impulse, the mode shape entry for first mode, second mode and third mode, and then Fa is being multiplied. So this whole thing becomes the amplitude of impulse, and this is K is modal stiffness times 1 minus cos omega t. So actually we are considering each mode as a single degree of freedom system. We just need to identify what is modal mass, so replace m with that modal mass. What is modal stiffness? Replace K with that modal stiffness. What is the amplitude of applied loading? Replace P naught with that amplitude, right. So with these changes we get this equation which is the response. When we put I equal to 1 and put the real numbers, this will become the equation for Q1. Similarly Q2 and Q3 can be determined, and finally we can construct the Q vector. Q vector will be Q1, Q2, Q3, and let's take that Q vector again to U vector by multiplying with the capital phi matrix. So when we apply that equation, capital phi matrix times Q vector, we get the U vector back, and each entry in the U vector can be again written as the sum of the contributions of 3 modes, just like the free vibration case. So I write u1 of t here. So this is the first term in that multiplication when we carry out that whole thing, second term and third term. Currently the numbers are not entered. If you just put numbers, actual numbers, you get this as u1. You can see that this is the contribution of first mode, second mode and third mode. When you plot individual terms, the same pattern you can experience. First omega 1 will have some omega, then this will be like this and this will be even smaller like this, right. So even you can calculate now forced vibration response using this modal analysis technique. The only requirement is that you have the solution of that single degree of freedom system, this equation. So currently I give a classical loading which is the impulse loading. So I already had the response available for that impulse loading. But if for example I give this Q1 of t as a random loading, then you will have 3 random loadings as R1, R2, R3. Then the solution of each modal SDF system will require either Doha-Mill integral or step-by-step direct integration, but the overall method will remain same, right. The difference will be that instead of using this expression, you will be getting Q1, Q2, Q3 from Doha-Mill integral or from step-by-step direct integration. But once you get that, you again bring the solution back to U coordinates and finally get the final solution in U coordinates U1, U2, U3. In that case, when the loading is random, it may not be possible for you to write this equation for U1 because you will be actually performing numerical integration. So you will be automating that calculation step. So actually you may not write that whole equation for u1 if the loading is random, but the method will be same, right? So principally now you can handle any multiple degree of freedom system if you are given with its m and k matrix, right? Because that is what is required to first calculate the mode shapes and time periods, and that will become the starting point of your modal RHA. So just to summarize, as I have explained earlier also, that you don't need to carry out the analysis for all modes. You can just consider first few modes and just put all other modes equal to 0, right? So ideally the equation is summation of phi I q I from I1 to capital N, but practically you can simply keep it from 1 to k, where k is far less than n. If the number of degrees of freedom are 10 million, you just need first few modes, 5-6 modes may be enough, depending upon the building height and complexity and also the configuration, because if you have a regular frame building where the mass is actually lumped at, most of the mass is lumped at floor levels, first few modes is enough. But if you have a building with a lot of shear walls and irregular shear walls, for example, you may need to go maybe 6-7 modes or higher than that, right? Actually for those practical cases you will not be doing it yourself, the program will be actually performing that analysis for you. But see, when you just consider, for example, first 5 modes, you will be actually using the masses corresponding to those degrees of freedom only. So only those degrees of freedom actually. So mostly in practical cases, the program lump the story mass at a master node at each level and slave all the nodes to that master node. So the lumped mass matrix is created automatically in the program, and the modes are calculated from that lumped mass matrix. So the program also doesn't use all modes to solve for modal RHA. By default, I think in ETABS the option is 12 number of modes, which is, if the building is regular, first 3 modes in all 3 directions, x, y and torsion direction, are covered in those 12 modes. But if the building is irregular, then you may need to increase from 12 to maybe 20 or 30. So, no, but not more than that. There will be a point when adding more number of modes to your modal RHA analysis will not increase your accuracy. So ideally we have to go for n number of modes, but we just keep our solution to k number of modes, where k is far less than n. Lower modes are more important, higher modes have lesser and lesser contribution, right? First few modes are more important. But one more important thing is that all of this method, modal RHA, is a linear method. It is not a non-linear method. So if your computer model has a capability to simulate cracking, yielding and all those inelastic phenomena, then you cannot apply this method. Then the direct integration is the only method available for dynamic analysis, non-linear dynamic analysis. But for linear dynamic analysis, you can either go for modal RHA or you can go for linear direct integration, right? So you will deliberately keep the higher modes, you just put their q equal to 0, and the solution will only consider up to kth mode, right? So this k prime is this q prime is a modified q vector with all the higher modes set equal to 0, and you only consider first few modes. The solution will be far quick compared to the linear direct integration method. Effect of damping we haven't considered in this modal RHA. So actually if your capital phi transpose times capital C times the capital phi again, if it is a non-diagonal matrix, your whole scheme will not work. See, the original governing equation of motion is mu dot dot plus cu dot plus ku equal to some q of t. vector. Now you haven't considered this C matrix up till now, but you used the orthogonality property of mode shapes with respect to mass matrix and with respect to K matrix, and this will give you the uncoupled equation of motion. Now if the damping is added to this scheme which we have just introduced, and if this matrix is also diagonal matrix, then our uncoupling will still work. We will still be having uncoupled equations. But if it is a non-diagonal matrix, then our equation is still coupled. Can you get that point? If I go back to the very first slide where we get those uncoupled equation of motion, we ignore damping there and we only use the orthogonality property with respect to M and K. So in order to this modal RHA to work, you have to have mode shapes which are orthogonal with respect to C matrix also. Otherwise this uncoupling will not work with damping. So here you can see this is actually what? Capital Phi transpose into M into capital Phi times Qi dot dot, Q vector dot dot, and plus this is what? Capital Phi transpose into K into capital Phi into Q of T vector is equal to some capital Phi transpose into Q of T vector. So there is no damping term here. So this product we write it as a diagonal matrix because of orthogonality. This product we write it as a diagonal matrix because of the orthogonality. But if we have damping term in between, that damping term should also follow this orthogonality if this scheme has to work, if this uncoupling has to work. So the capital Phi transpose times capital C times capital Phi again, this should also be a diagonal matrix. If this is true, then we can still have uncoupled equation, right? So here you can see that when we have the damping term, there will be an additional term here, capital Phi transpose into capital C times capital Phi again times Q dot vector. This is an additional term when you add damping, and if this product is diagonal, then we can still have uncoupled equations. So the modal RHA will still work if the damping matrix is following this condition that capital Phi transpose into C into capital Phi is a diagonal matrix. If damping matrix follow this condition, we call it classical damping, and if it doesn't follow that condition, we call it non-classical damping. So it means that in order for modal RHA to work, we should always have classical damping, right? Otherwise this uncoupling may not be possible, and therefore modal RHA method itself will not be possible. So that's what I just wrote here at the end, that this method is not applicable to non-proportional damping or non-classical dampings, which means that this product is not a diagonal matrix. This product have to be a diagonal matrix in order for this method to work. So which means that we should construct C matrix such a way that mode shapes are orthogonal to each other with respect to C matrix also. We have seen that they are orthogonal with respect to M and K, but they should also be orthogonal with respect to C matrix in order to have this method. So therefore the damping should be classical damping, which means that this condition that this is a diagonal matrix should be true in order for this method to work. If we have non-classical damping or non-proportional damping, then there is a complex modal analysis which can be used for forced vibration response, but we will not go into its detail. ETABS have two damping models. I will explain maybe in next class. Both of them are proportional damping models, right? So both of them actually follow this condition. Though actually having a damping model means that having a method to construct C matrix, right? So ETABS have two methods to construct C matrix. I'll explain them maybe in next class, but just I want to to give you the definition of classical damping or proportional damping. One way to get proportional damping is, and having the equation of equilibrium uncoupled, is that if we can write C matrix as a proportion of mass and K matrices. Imagine that you can construct C matrix by adding a constant, by multiplying a constant to mass matrix and then another constant beta to K matrix. Now mode shapes are orthogonal with respect to M and K, and if you can construct C matrix by adding M and K matrices, the resulting C matrix will, all mode shapes will orthogonal with respect to that C matrix also, right. So one way to get proportional damping or classical damping is to write C matrix as a function of M matrix and K matrix. So this is one way of constructing the C matrix, that you set alpha and beta such that you get the matrix which is representative of the actual energy dissipation. So I will explain in any next class that how we actually find out that alpha and beta, which is the most representative of the level of energy dissipation in your multiple degree of freedom system. But the idea is, which is also sometimes called as the mass and stiffness proportional damping, M and K proportional damping, that you write C matrix as a function of M and K matrices. So you can, if you can have already M and K matrices, you can construct C matrix directly, and that C matrix by definition will be proportional.